All right, guys, so let's get started. So basically, remember this problem on the monitor here, which is the problem we started solving the other day. And this is for single degree of freedom, but for force vibration. You have a force on the right-hand side. So we went through the whole theory. I think it took us like a whole class. And so let's see, that's what we have over here. So we went through all the stuff over here on May 25th. So we ended up saying that the solution is going to have two parts. One is going to be the homogeneous, the one is going to be the particular. We did everything symbolically. All right, and then we started to work on a problem. Okay, with some data where the force excitation would be 10 cosine 5t. So with this, with all the algebra over here, so the final homogeneous solution to be of this form. And then we need to do the particular solution, solve for those coefficients AP and BP, substitute. We have that equation over here. So at the end, we had that the total solution, homogeneous per particular, to be equal to the equation you can see on the screen. Okay, so the next thing, once you have the total solution, you need to solve for the initial conditions. You need to solve for C1 and C2 using the initial conditions, right? When we did this stuff, I remember we didn't do it on the piece of paper, we did it using Maple. Okay? So let's go and open the Maple file, because actually, today, when I was going through the notes from last time, I found out that we had one little error. We replaced a multiply by a plus sign, and that changed everything. But I uploaded the correct files into Canvas now. But let's just go and look at the files. So, computer, let's see if I log in. Okay, so the file is still here. So these are the original files, so maybe we can use, yeah, I can show you what's the mistake. So this is the original file. I actually saved them on my shared drive, so it will be something different uploaded, but this was for the data, we have this stuff. What is the mistake here for the homogeneous solution? This, instead of being a plus, needs to be a multiply. So you see that little things change everything, because then you have this, we add the, so this is the homogeneous solution, this is the particular solution, we add them together, correct? So in order to find the initial condition, we apply the condition that x equals 0 at 0, and that the velocity was 0 at the time 0, no? Okay? We did this, and we had those two equations. So these are the general equations. Now you see at t equals 0, I say that equation 1 equals x, equation 2 equals 2v, and then we solve for C1 and C2. So here you see what was the mistake. These are the new values over here. Maybe I need to make this bigger. These are the new values. This is what we found last time by having that type of error, no? So all I did was basically to replace those equations there by doing this. All right, and then I did this, and I did this part, okay. Okay, so now we have C1, C2. Oh, I guess I don't burn here. All right, we go here to restart. We have these values. And basically, Here we have the same mistake again. So basically the final solution will be of this form, okay? I already did the modification, so we don't need it. So now using this, really we didn't use this final form. What I use is this form over here, and then I put the values of the coefficients, okay? So after doing that, I don't know if you remember, we went to MATLAB. In order to do the plot. So this file is over here, but I already modified it, so let me just go to the modified one. I only change the values of C1 and C2, and that plus sign for the multiple sign. So this is this one, so let me see, open. I save it on the shared drive. As well, so I've saved it from the beginning. So this is what I have, MATLAB files. Okay, so basically it's the same file. I don't know why it's doing this. I hate when it's putting it that way. So now it brought me twice the same file.
Looks like it.
Okay. So basically you see the file, this will be the two values of the constant that we just calculated. This is the form of the homogeneous response, okay? This is the one of the particular. So this is the total solution, x homogeneous plus x particular. What I did here, a plot is, the first plot is to plot the homogeneous, second plot to plot the particular, third one to plot the homogeneous plus the particular, okay? So I guess we need to go now to
Editor.
editor.
Yeah.
Obviously, it's always like that. You try all of them and okay. So basically, here what you see is what is that what's happening with the homogeneous after a certain time, as expected, is going to 0. Okay. What's happening to the particular, which this one is the one due to the forcing function. In this case, 10 cosine 5t. So it's basically the cosine function, no? Over here all the time. So what's going to happen when you combine both of them? Obviously, the total response is going to be disrupted, if you want, until the homogeneous solution dumps out to 0. And then this should just be this one. Okay? So you see, basically up to maybe 30 seconds, here you see the response will be changed because you combine this part and this part. But after about 30 seconds, the response is basically periodic, like this one. Okay? So we had that discussion saying that in most cases, obviously depends on the application, but in most general cases, do you really care about the homogeneous solution, or do you care most about the particular solution? In most cases, you're going to care about the particular solution, because this one is going to go to 0 anyway after a certain time. All right? Okay, so let's just complete the class notes with the correct data, and then we're going to solve this problem again numerically. Numerically, the numerical solution should give you what? The numerical solution should give you the homogeneous solution, the particular, the final solution, or neither one.
Would it be just the particular?
It would just be the particular, but will the beginning be like this one, or will it be a little bit disrupted like this one?
I think if you just type in the differential equation, I think it'll be purely the particular. That's my opinion.
It will be this one, but remember, the time it will take for the response to converge to the final solution will depend on the guess that you do for the initial steps, no? Your initial conditions to solve the differential equation.
Mm-hmm.
So for example, if you say that the initial steps is 1, it's going to take longer to dump out to this one, no? All right? So it's probably going to look like this one, but this part is not going to be this part. It's just going to be due to the initial conditions and not to the homogeneous part. Okay? All right, so let's go on now to the .com. So, oops, I cannot do, okay, so let's do this. So determine C1 and C2 for the initial conditions. These are the initial conditions over here. Let me know if you cannot see properly. So, okay, this one at the back. Oh, a second. This. All right, so I'm gonna put here from Maple file, which is on Canvas, you're gonna find that C1 is equal to 0.0, oh wait, 4. I have here the one on the class notes, but I don't have that file open. Let's see if I try to print it. 0.0434 minus 0.003657I, and C2 would be equal to 0.0434 plus 0.003657I. Okay, so substituting into, let me just put an end to it, into this equation here, which is all the way to the top. So substituting into that equation, let's put this one star, put it into star, the problem, final, solution is obtained. Okay, so I will add, so this is, today is what, May 30? Okay, so I will add, I put this one on the scan anyway, but I will put those files that we had to find A sub P from this expression on the solution, and the file we just used to find C1 and C2. I'll put them at continuation. I probably would like to put also the MATLAB file that we just created. Will also be on the class notes, but again, I uploaded all this stuff into Canvas. Okay? So maybe let's do a quick sketch over here. All right, so the final solution, if we kind of plot it, if we do the homogeneous, it was the time between 0 and I think we say about 30, I think we say about 60 seconds, but about 30, I think the response was damped out. So if we plotted the homogeneous, I think the solution would probably look something like that, no? Or something like that. Then when we plotted the particular solution, so this one we know is going to be periodic. It's going to be, remember what's going up, so it will be cosine of, this is 1, so it should start about from here probably. Was looking something like that. And then if we plotted the total solution, so the beginning will look a little bit different. We'll start from here, let's say, and then we'll start maybe from here a little bit, something like this, something like this, but then slowly we'll start going there, and it will stay periodic after about the 30 seconds, okay? After 30 seconds, the response was basically that out. All right, so we say depend on the application, but in most cases, the homogeneous, you don't really need it because you see that after a certain time, it's just going to be equal to 0, and you really just care about the particular solution. Okay? So this would be page. All right. Okay. I will have to scan this later today or tomorrow. Well, actually, I could have just showed you that figure. I have it here. This is the figure that you have. So on top you have the homogeneous. Or here you have the particular. Here you have the overall solution, and this is the numerical. Okay? Actually, let me put that one instead of the page we just did. I'm going to do better. You can do both. Okay. So what would be the way to solve the numerical solution for this problem? So let's go over here. Numerical solution. So in this case, what is our equation is mx double dot plus cx dot plus kx, let's say, will be equal to f. So what was the assumption we're doing on the other programs in order to solve, the assumption, what was the process we're doing with solving this problem numerically?
You'd put the, you'd use the function of z.
Okay, so basically what we're doing is we assume y equal x dot, or what we say z will be equal to x dot. So this will be the initial condition. This is the initial displacement. this will be the initial velocity, okay? And then we say z dot will be equal to what? X dot a dot. So this will be what? I think that's it. You can just say that. Okay, or if you want, I can write it. This will be y. We don't need this one. I think this part was just enough. Okay, so now we rewrite. So we had what? We had that x double dot was really equal to what? Z of 2 and x dot z of 1. Okay, so we take the equation and we do the same process as before. We have x double dot mx double dot plus cx dot plus kx, but this time what is the difference? That this side, instead of being 0, is equal to f. And this is in function of time. So we need to write in function of x dot, so that means that x double dot plus c over m x dot plus k over m x equal to f divided by m. Or from here you could write that x double dot will be equal to f over m minus c over m x dot minus k over m x. Yeah, so this will mean what? That z dot that is equal to x dot x double dot. I mean, this is exactly the same thing we did last time. Will be equal to what?
X dot on the top.
On top, and then on y? F over m.
Yep, minus c over m x dot minus k over m x.
Minus, but x dot is equal to what? Is equal to the z1, no?
Actually, no, that would be z2.
No, z2 is the x double dot. Is this one, z1, z2,
No,
no?
that's z dot 1.
Z dot. So it will be z2, you're correct, so I'm gonna erase this one, so. Let me just rewrite this line over here at the bottom, it will be more clear. So this one will be f over m minus c over m. We need to use the z function, so that will be z2. Correct? And then we're gonna have minus k over m. The x will be
z1.
z1. And this will be the x dot, which is
z2.
z2. Okay, so I have a little bit here because I don't have all the data with me, but now what we need to do is to do what? Create the MATLAB file for this, no?
Yep.
Okay? So probably we can use some of the other ones, or the old ones. So let's go here to the MATLAB files. So home, are. Can I eliminate this stuff? Can I eliminate this one here? This. Okay. So let's close this one and let's just say now we open. So open file. We can modify. So this will be we have example free column dumping, example free dumping. Let's set this file as example force. So for force instead of free force dumping. So let's see what is the data for this problem. Do you guys have it? I think C was 1 if I remember when I did
Yep.
it today.
C was 1, M is 5, and K is 10.
Okay. So 5. So now the problem is that we have the T. Okay, we have the T over here. Our initial conditions were 0 and 0, I think, no?
Yep.
0 and 0, and let's call this one D function. I think we have D function 1 and 2. Let's call this one D function 3, no?
Yep.
The other component. This here is the analytical. We're not going to do this one in this problem. Just going to do the numerical solution, which should be the second part. So let's just do this part over here. And if you want, we can do this one. Yeah, this should not show anything, but let's leave it. I'm curious to see how this is going to do. So now we need to open the function 3. So let's set this one. So open. Let's open that one. Let's call it right away so we don't break it. The function 3. Save. So we need to change the data that was 5, no?
Mm-hmm.
Then 1.
Yeah.
I think that we don't need it. This was, yeah, this I wouldn't need it. Oh, but what is the function we need over here?
Over where, sorry?
We need the function f, no? So what is f? Remember
10,
was
10 cosine of 5t.
10 times cosine of, I mean, you can put capital omega, but in this case, let's just do a tweak, okay? 5t, so the problem here is that we're gonna have to put the time interval in here, because otherwise we're not gonna be able to calculate t, cosine, the f function. So what was the t we used on the other one? T equals to 0, what was the time step we used?
I think it was 0.05 and then 20.
105, okay, so let's use that one. It might not be enough. The other one we use 60, no? On the analytical in order to see the solution. So maybe use 60 over here as well. Hopefully that should be enough.
Might need to do that in T-span as well.
Yeah. So 60, we did this, so D for 5, the function 3, we did function 3. So now what do we need to change over here? We need to put here f divided by m minus c divided by m times z2
Mm-hmm.
minus k over m z1 return.
Yeah, in the system parameters, you still have it labeled as mu. You need to change that to C. Not there.
Oh, here.
Yeah.
Yeah.
And
Should be C.
also, you probably need to change the function to defunct3 or MATLAB's going to explode.
Okay. Hopefully it's not going to take a long time like last time, no?
Hopefully.
D function 3. So this should put the value on this one. Hopefully this time step is one enough.
Just want to give it a shot.
Okay, we can do always go and try, no?
Yeah.
So this would be the function. All right, so what happened here?
Um,
4D45.
Oh, one thing I found when I was doing this for the homework is that when you put in the function handle to ODE45, it actually prefers to have an @ sign before the name of the function instead of quotes around it.
In this?
Yeah, so if you take off the quotation marks and instead just put an @ symbol in front of defunct3.
And add, say, a plus sign?
No, an @ like
Or add this?
yeah, that.
Yeah, I have no idea. Hopefully.
Yeah, I think it's something that came with one of the new updates. Ah, crap, didn't work.
That's why I didn't do it.
Interesting. Now let's see what the problem is.
That doesn't change anything. Okay, so let's
Does
see.
not.
We never had that problem before, so what do they say? OD15 sets argument to 1. Line 18. They want it to be 0 or what?
Maybe not.
Yeah, because here we solve numerically. So we cannot put 0. Let's
Oh,
put
no.
here 1.
You added another line, so it's actually referencing line 19, not line 18.
What did I do?
At the top, you added an extra line somewhere. Yeah, you added that.
Oh,
So
this,
push
yeah.
everything down, so it's just the ODE is
Okay,
wrong.
yeah, but I think the problem is here is the initial condition. It cannot start from 0. I think this is the problem.
Mm.
Oh, hopefully.
Oh, yeah. Oh, it's still-
Okay, let's go back to this one because you're probably right, you know?
Yeah, I don't know, maybe not. I'm not
But
sure
you
what
never know,
version
yeah.
example we're using.
Okay, so what's the problem now? Error line 87. Okay, but that cannot do anything. On line 115, on line 19.
What is in the function again?
Can be this, that, the T function at the time. Well, let me try to go and see
Oh,
what I
the
did before.
town might be missing brackets.
That, and also it could be, should it be 5 dot times T? But-
What I can
but
do
at the same time,
here,
that's not giving an error message in that, it's giving an error message in the functions. Yeah.
I've always put brackets around the.
what I wanna know if
It's
it's,
not
here is
even,
giving,
but-
what I'm curious to know if here is giving one value or is it giving a lot of values?
Yeah, exactly.
So that's what I'd be curious to know about, yeah. Because you only
You have
give
to-
one value for that. That's probably what it is, no?
No, it looks like it's multiple values.
Yeah, but is it taking, so for example, is in here one value, and then it's taking the first two values, or is all the time taking?
Where's the side of that? So you can check what's inside the New Jersey.
Let's see if,
He's very back, right?
let's see if
Yeah,
we pass this
that's
one.
allowed.
You didn't go through this one, huh?
Maybe.
Oh,
Did you go through the first step, or?
Now it's got problems with defunct 3.
You did not clear the child wants more, so CLC. I have here all over here, no, this one at the beginning. Yep. Okay, so the funny thing is that it's get to the figure. So here you see it's taking all those values. I think that's the problem, so how can I do this one here? Or is that F, and that's for F? Let's see what I did over here. What did I do? Okay, I'm just gonna change something. I don't know if you're gonna change anything. Here is taking the vector instead of taking one value at a time.
No.
I think that's the problem, so we need to eliminate that one. So So, let's see on this one.
Yeah, probably need to do some dot multiplying or something.
Yeah, might be that. Same as before, so that didn't change anything. So the dot over here, we can change.
And probably inside the parentheses of the cosine as well. Probably.
No. All right, interesting. You know what? Let's try something completely crazy. If I take it out, will it solve it?
You're just trying to call
Good, because it does pass the time now.
it. There, that's weird.
All right.
Okay.
Okay, but that looks more like a one-on-one, no? So you see, everything comes from our initial guess. So let's go this one, read on, let's eliminate. I mean, you see this one doesn't make too much sense in this case, no?
That's cool.
I mean, let's do it. Let's run it once more, but now, so if we have a high conversion, let's move this, let's say, to 0.5. Probably should have to go faster. So we run it. So this one, what's happening? This would be our initial guess. It's getting crazy because it has the damping, it needs to converge, and then what's happening at the end? It's just going to stay in a circle and ellipse, no? For the periodic. So that's what you see. And here you see basically what do? We go from 0.6, before was longer, and then if we do it this way, how long does it take for this to go to the response? Again, it's about 30 seconds, no? And you see it's high amplitudes over here, and then it goes to the amplitudes on this case, all right? If we change again this one to 0.1, probably will be a lot smoother, no? And you see this one kind of tells you are converging a lot faster. So this one you see, I mean, still, I mean, it looks better than before, no? So the convergence of your response will depend on your initial guess. Okay? So now let's go to the other extreme. If we put here 2, what are we going to get? Something periodically, no? It's going to take a while. You see? It's going to take a while for the response to damp and to get there. Okay? All right, so let's save this. So the function 3, so all this stuff should be saved. So let me be save. Oh, right, okay. Let's close this. I'm going to close this one. I don't know if I can upload it if they're open, so that's why I'm closing them. And let me go here and upload those files now. Okay, so I don't know if you saw over here on the videos, the other day I uploaded the class notes for May 16 to 24. Okay, I put it over there. This is the way I did it today because last time I had problems with the laptop. Again, but so here we will go. Now we go here to MATLAB files. I also put here the Maple files over here. This is Maple files. So let's say here, edit. What they are doing, they erase kind of good. So maybe we can put a title here. This was for, yeah, this is force vibrations. And then we have here file. So, no, that's not what I want. I want desktop. 100, summer, MATLAB, now what do we do now? The force, no, this one? Upload. And this one goes with the D function 3, no? Which is this one. Okay, so maybe let me add something here. Numerical. This is a part numerical. This is the analytical files, okay? And we put here the same. All right? Okay. Okay. So it will be page. Page 9, page 15. All right. So next. Because from now on, okay, here we went in a lot of detail because the first time, so for the understanding it's important to go slowly, okay? But now what we're going to do is just solution of previous problem using the what I call the exponential notation. Okay, so basically, oops, you should let me know that I wasn't there. Using the exponential notation. And that's the notation we're going to be using now all the time, okay? So this is a problem where we have the force vibration. We have the spring, we have the damper, and we have here the force F of t, where basically we have what? Same problem as before. M equal to 5 kilograms, K equals to 10 Newton meters, C equal to 1 Newton second per meter, and F of t was equal to 10 cosine 5t, where omega is the 5, no? This one. Okay, so obviously I'm not going to redo all the details. We're going to start going a bit faster. But the equation of motion for this is what? Is mx double dot plus cx dot plus kx equal to F. Alright? So we use exponential notation. What do we say? Assume. So assuming the solutions to be of which form? X of t will be equal to what? X of naught e I capital omega t. We say we want the response in function of the forcing frequency, no? Why do we do this stuff? Because we know that the forcing force, even though here is 10 cosine, the general form would be what? F sub naught EI omega t. So if you want now, I start giving you the heads up. What is really EI omega t equal to?
Cosine omega t.
Cosine omega t plus
Plus
I
sine.
sine omega t, no?
Mhm.
So really, if we wanted to solve these problems, I give you a little bit of heads up now, we'll be taking what? Just the real part of this solution, no?
Mhm.
And this will be equal to our 10 cosine omega t. Alright? So that's exactly what we're going to be doing. Alright?
Okay.
So we assume the solution. Once we assume the solution, what do we do?
Ah, yes.
We substitute back into the equation of motion.
Yes.
Okay, but I'm not going to do a lot of details. So we substitute. Into equation of motion, and basically, if you remember this, so all this part of the response in function of x, no? So x will have in common what? X EI omega t. What will be for the first one? What will be x double dot? Will be equal to minus m
Omega squared.
omega squared. Now what will be the one of the damping? Plus I
C omega.
C omega plus K, no?
Yeah.
And then what will be the one of the force will be F sub naught EI capital omega t.
Mhm.
Okay, so remember we did all this stuff in detail. So why do we do this? Because why do we assume both of them the forcing functions? Because at this step what can we do?
Cancel e to the I omega t.
We can cancel this one on each side. And now what do we need to solve for over here to find the final solution?
Solve for x naught.
Well, x naught, and we see over here. So x naught would be equal then to what? To
F naught over everything in the brackets.
f naught divided by the m omega squared plus I c omega plus k. Okay, and this is correct. You can leave that under this form. But let's see if I have the class note from the other day. But if you remember the class note from the other day, we can write this in function of the damping ratio, no?
Mhm.
So let's see if I have it in here. So this is the one from the other day. I don't know if that's the one we used, that's the other one before. I don't know, we did that the other day or the one before, no. So I think, might not be in these notes, no, it's not here, it should be on the day before. So, let me add these ones. So there we go. There we go. It was the day before. So basically, you see this is the solution. Can you see or not on the monitor? This is from the class, so let's say from page 37 on the class notes. This is the same expression.
Mhm.
Or not? Not exactly the same expression. Not yet. So let's go to the back. We go to the back. This is the same expression. Yeah?
Yes.
So I need to do substitution, and then I say, okay, you can write this under this function, or if we want to try to write this in function of omega n at the damping ratio. So this is page 35. Remember we went through all those pages here of algebra.
Mhm.
doing all those transformation. We multiply here by the conjugate at the top and the bottom, so you can write this under the square form. Then we rewrote, this is a general form. We had this expression for the x of naught, but we didn't stop there. We said, what about, so this is this form, one more page. Then we did this transformation over here. Some algebra, we wrote this under this form, and we have everything on the function of the damping ratio. We know those derivations, so at the end, what is the response equal to? Is equal to x of t, s of naught over m, h of m, ei of omega t minus phi, and the phi is the phase, no?
Mm-hmm.
With all these expressions over here. So that's basically what we're doing now. All right, and this is phi after we do more transformation. So that was page what? 30. About 35 to 39 on the class notes. So I'm just going to put it over here. That one. See pages 35 to 39. Page 52. So what do we have? We have x of t equal to f over m hm. I think here I changed the notation of omega squared, capital omega over omega n, e I omega t minus phi. Okay, and if you want, let's do it once more. Where, what was this equal to?
1 over omega n squared times the
Omega n squared outside, no?
Yes.
And then is the square root
Mm-hmm.
of 1, no?
Yeah, it's 1 minus the ratio squared.
Yeah, capital omega, everything squared, plus 4,
Mm-hmm. Psi squared, ratio squared.
oh, psi squared as well.
Mm-hmm. At least that's what I got.
Yeah, that's what it is. Okay, so now it looks like one complicated. And and what was the expression for phi over here, since you have it?
It was the arctangent
Yeah.
of -2 psi times the ratio frequencies divided by 1 minus the ratio frequency squared.
Okay, thank you so much. Okay, so I know this is a complicated expression, but we can say here in the present problem, f of t is equal to what? 10 cosine 5t, no? Yeah? So the function of the cosine.
Yes, sir.
Now, what is the general form of f of t? We say
F
was
naught e to the I omega t.
f sub naught e I to the omega t, which Yeah, we can, let's do it this way, so we know this will be equal to what? F sub naught of cosine omega t plus I sine omega t. So if we compare this expression with all this one here, oops, with this one, just this side, not this side, what can you say?
F not equals 10?
Yeah, be careful here. It's not going to be exactly that. But what I'm trying to say is that S of t equal cosine omega t, if you want, trying to say this will be equal to the real part of S, the real part of S of naught e I omega t. Yeah? To the solution. Okay? So at the end, if we know this solution over here, or yeah, the 10, okay. I'm going to say that then x of t of the solution will be equal to the real part of the total solution over here. That will be f sub naught over m h sub m capital omega over capital omega of ei omega t minus phi. So the total solution at the end is x of t equal to f sub naught over m h sub m omega over omega n. So what will be the real part equal to? Cosine of
Omega t minus 5.
omega t minus 5. So what I'm trying to say, maybe here I don't want to create any confusion, maybe just put here f, eliminate the 10 because it's creating the confusion. What I'm just trying to show is that you need to look at the real part, no? Of the solution, not at both of them. So you want to eliminate this and this. So at the end, this would be the solution. And let me put it here. What was the general form of the solution? At the beginning, what was the assumed general form of the solution?
An exponential. Or
It
harmonic.
was the, what I would say was, yes. And the initially assumed was x of t equal to x sub naught, no?
Mhm.
ei omega t, so if we just take the real part, what will we get? X sub naught, oops, x sub naught,
Cosine omega t.
cosine, correct, cosine omega t, no? All right, so since you mentioned before, what should really be the amplitude of the response? The x sub naught really is equal to the f sub naught over m h to the m omega t. Yeah? So if you want, page 52, page 53. I just try to put some values and then we can go to the, we can set it. So the amplitude of the response x sub naught is equal to, so what? We have x sub naught should be equal to what? F sub naught over m, h of m, capital omega over omega n. All right? So something important on the assumed solution here. So the solution we have here, the solution we have at the end, x of t. X of t, if you want, we have f sub naught over m, hm omega n cosine omega t minus phi, or you could say x of t equal x of naught cosine omega t minus phi. Where x of naught is this. I know you know the answer now, but maybe in a few days you might forget. So that response here, x of t, is that really the full response?
No, it's just a particular solution.
So this is really just x of t over here is only particular solution. So what's important here to realize is that when solving using the exponential notation, comma, we are ignoring the homogeneous solution. Okay? It doesn't mean that you cannot solve the free vibration problem using the exponential notation. But what I'm trying to say is that I'm not 100% correct. What I should say is that here we are really just solving for the part where the right hand side is not equal to 0, no? And for that, and in order to do that, we use exponential notation. We could use exponential notation also and have the right hand side equal to 0. But then it would make no sense because, I mean, it would be a bit confusing because if we do that, then what would be the assumed solution? What will we use over here? If we use the free vibration product, what would be the solution? It would be x of naught again, but instead of the forcing frequency, you have to use the natural frequency.
Okay.
Okay, and then everything becomes complicated. And what is the idea behind ignoring the homogeneous solution is that no matter what, it's going to go to 0 after a certain amount of time, no? Okay? So unless your application requires to know the homogeneous solution, it doesn't matter because it's going to be 0 anyway, no? After a certain amount of time. So from now on, basically, in 99% of the problems, we're going to be ignoring the homogeneous solution because we know that part of the response will be damped out to 0 after a certain time. Okay? All right, so for this problem, we didn't do it, so maybe let's do it here. What would be, and we can go and check with the numerical solution or the classic solution. So let's do over here. Okay, so numerical application. So what would be f sub naught? What's the value for f sub naught?
Would it not be the amplitude of the forcing function?
Yeah, which is?
10.
Okay. 10. What is m? What is it, 5?
Yeah.
5. And then we're going to have to find, so capital omega is
Also 5.
5, and omega n is square root of k over m, no?
Square root of 2.
Square root of 2. Okay. Because k is 10?
Yes.
Alright. So what about you go and do, guys, please, the numerical application for me for, so we know that H, so we know F, okay, so X, so X dot will be equal to what? Fm, and then you have all this long expression here, which is the 1 divided by omega square of 1 minus and this one was plus 2, no? Square.
Could you move the paper up, Professor?
Yeah,
Thank you.
I think that's what you gave me, no?
No, it should be 4xi squared.
This one?
Yeah,
Okay. 4 sine square, and this one is square as well or not?
yes,
Okay, and this is 1/2.
yes.
So you do numerical application, what do you get? Yeah, it's long. Sorry for that, guys, but
That's all right.
I mean, the best thing you can do for this thing is what? You write once the function in MATLAB now, and you will know it. Maybe I could do it. Do it too, but- Let's do it if you want. Yeah, let's do it. So home, over here. Somebody can help me, computer. Alright, so let's see what happened over here. Let's see. File. Open. I think I can use this one here for stamping. So we have the data and say omega C,
Yeah,
omega D. We can leave T and erase all this stuff. So let me do anything. File, save as. For stamping, exponential notation. That's it. All right, so you have me over here. We're probably gonna need this anyway because, or not, I don't know. Yeah, let's try to do this one a bit more general. So I know we're gonna need this one. Let's see if we can make it work general. What is f? It will be f sub naught of exponential of I times omega t, no?
Mhm.
So we're going to have to put here, this is little omega, and then we need capital omega is 5. And f sub naught is 10. Okay? So it looks like it's fine over here. So M, so we need now to put the H. H equal to, that's going to be complicated to write this one, 1 divided by omega n squared, is that what it is? Divided by the square roots of 1, oh, I have an idea. Let's call R, what was the ratio? Is capital omega divided by small omega, no? Guys, help me a little bit here. R is capital omega divided by little omega, so it will be 1 minus R squared, everything squared, plus 4 times psi
Squared, r squared.
times r squared. And that should do it, no? 1 divided. We find out. So now we want to have x of t, the final solution, to be equal to what? The real part. Let's do x over here first, I guess. What is, or x of naught is f o divided by n times h, no? And then the final solution would be to x naught times exponential of minus I times omega times t minus 5. I forgot to put the expression for phi. What is phi? You give it to me.
Arctangent.
Yeah, hold on 1 second. No, I put this
No
one.
problem.
Okay, I put it here. So phi is a tangent
Of negative 2 psi r
okay,
divided by 1 minus r squared.
so let me just put here, this will be the real part of all this stuff. Let's see if it works. You think it's gonna work?
We can pray.
T comma x. All right, let's try. That's all we're gonna do. Oh, psi, we didn't define psi. Is that the only problem so far? Oh, that's very different.
Hey, hey.
I'm surprised we're gonna work that fast, huh? So basically, what's important here to see is what? When we see on the figure what is the value of the amplitude is about 0. Looks is right above 0.08, no?
Yep.
And when we calculate the x of naught, I guess I can find it here from this value here.
Yeah,
What
by
do
our
you get for this?
calculations, yeah, it should be right in the neighborhood.
It should be right there, no? So hopefully it is. I mean, 0. Actually higher than what I thought, but 0.0869, no?
Yep.
Okay, so basically you see that the response will give you that, all right? So this is just using the exponential notation. Let's see now what happens if we go and open the file we had before, which is the false vibration, this one.
Mm-hmm.
We didn't go and check, no? But if we go this one and run this one, I don't know why I kept that figure. Okay, we went to 2. Let me change here something, okay, so we will go faster. So what about we put here 0.1, is that okay?
Sure.
Oh, we go a lot faster. I don't know why I keep that one. I'm gonna remove it. We can do it. Let me run it. So over here, we need to look over here, just this section, no?
Mm-hmm. And it could conceivably be 0.08 something.
Yeah, what would be the way to find out this one? Probably, is there a way to find an amplitude?
I don't know it, but I know it exists.
Okay, a strange way to do it probably would be, oh, this is the numerical we did on this one, no? Yeah, this was on the numerical with this one. What could we do over here? Let's say we say, so let me call this one x2 will be equal to z
Z colon comma 2.
Yeah, but what I'm trying to find is, let's say, I have no idea how many points we have, but let's say 4,000 to the end. comma 1. So basically what I'm trying to do is what? Ignore the first part, no?
Mhm.
All right?
Hello. Are you looking for the time values or for the position values?
Right now I'm using for the time values, but
Okay.
what I'm trying to do is this. Time, so will be that what? Oh, I need to have, okay, so it will be the same thing. Z of 4,000 to the n. Maybe I should do that. Should I just put a variable there? Comma, no,
Yeah, comma 1. If the
comma 1. And then here I put the same thing that I put x2, no?
X2 is the same thing as that.
I think you also need to do this.
Yeah, if you do.
I'm trying, no, this is the one of here, so this is the time, oh, so I should put the,
Yeah, make that 2.
yeah, but now we will do the, okay, so let me just do this. So I'm gonna show what I wanted to show anyway, but, so we need to do this one, want this to be 2. And now maybe I should put now,
Yeah.
what do we have any figure?
You need to put it in the not command window.
Not put the semicolon at the end?
No, because you, yeah, I don't know.
Looks like the figure should be open.
Should
No,
be.
you need to not, it's in the command window, you have to put it in the function, or in
In the editor window.
Yeah, editor window. You're in the wrong window.
But which way do I go now?
No. In MATLAB, you need to take your function and put it above, because right now you're in the command window.
Yeah, up in that section.
Yeah.
Oh, to put this stuff in there?
Yeah.
Yeah, but I have to do this one in here anyway.
Yeah, it should still work. The little one, yeah.
Why is it not showing the figure?
I don't know.
I mean, let's see this. We don't need really the time. I could just do plot x2 really. See if that's gonna do it.
Actually, then it might be easier to read the amplitude.
Why is it not doing it?
Looks like, is there a separate window?
Is it hiding at the back?
No, doesn't look like it.
I think you have to put it in there.
Maybe you do.
Because I think it clears it every time. Like, it's not, the extra is not saved.
Okay. Anyway, let's run this one over here if you want. Yeah, let's do it here if you want. So if you want over here, okay. What am I trying to do is what? I'm trying to eliminate all this part of the response, no? So it looks like if I eliminate half of it, so let's
Actually, an easier way to check the amplitude, run the program one more time. On that phase plot, it should be the thickest part of the line. Shouldn't that give you the amplitude, just the distance between the two position values?
yes, we could do that way as well. Yeah. Yeah, okay, what I want to say is that maybe you can eliminate this and then you can just say, give me the extremums, and you add them together, because it will give you this one and this one, no?
Mhm.
And you know it will be periodic. So, I mean, do we need to do it in MATLAB or do you think you can do it? Maybe
We
you
can
can
check
check.
it out.
I mean, you can see more or less that it looks like it's correct, no?
Mhm.
Okay, we could zoom in. Will you change the figure? Oh,
Oh,
Yeah,
yes, very
that's it
nice.
about.
so this will probably give you about what, like 0.
0.809.
Yeah.
Oh, so the amplitude is only this part, it's not all of it, it's just this part, the
Yeah.
0.08. So let's see if you keep zooming, it will give you.
Yeah, that's it.
So, but you see, this one went a little bit up, which is not very good, no? Can I go now to the right, zoom? Fine, why are those keep changing? Huh?
Might be a little bit of leftover influence from the
Yeah.
homogeneous solution.
Yeah. I mean, the more you go to the right, the more it's gonna be accurate, no?
Yeah.
But you see, yeah, it was what, 0.06 something?
Yep.
So
So,
we'll go here and
It's about.
it's somewhere over there, no?
yeah, 0.869 was what it was.
869, so
that's
basically over there you can do it that way.
Beautiful.
Right? So basically you see that even the numerical solution will give you the correct amplitude. All right? So I guess that's all for today.
What?